Hello, today we are going to do a further more questions on Dirac Delta potential and a few revision also because yesterday very less people were attending the class. So probably I'll revise what I have done yesterday also. And so again, the topic would be Dirac Delta potential only. So this we are doing in the series of the discussion on one-dimensional potentials in quantum mechanics. So let us again try to do. Let us again try to uh, start from where we were uh, we were last doing Dirac Delta potentials. Okay. So I think the screen is visible. So I'll start off by just that problem that I was doing yesterday, and this particular problem we did yesterday only two problems. Yesterday we did a problem called as an attractive Dirac Delta potential. So yesterday we did a problem called as attractive Dirac Delta potential. So, and that particular potential was located at at origin. So initially it was located at origin. And then we did another problem where we shifted this particular Dirac Delta function. So basically, because you said there were not many people in the class, so I'm reiterating that problem all over again. So we were doing another problem that is at times called as your approximate solution to atom near a wall. So wall represents an infinite potential, and that problem needs a certain attention from your side. Okay, so the problem that I was doing yesterday, and not many people attended the class, is called as an approximate model of you can say model for problem of an atom near a wall. So an atom near a wall, and wall represents your infinite potential. So overall, what I would do is I would say that this particular problem, uh, this particular problem is represented by a potential given as Vx is equals to, let's say, minus V naught Dirac of x for all x greater than minus d, and for all x less than minus d, it is given as infinite. So what does it imply? It implies that for all x less than minus d, let's say this is my potential. So you have a infinite potential here at, let's say, x equal to minus d. And if you go for all x greater than d minus d, there would be a point where you have an origin. So yesterday I did the same problem, but with a different sort of potential structure. Only I have made a translation, nothing else. So again, I'm reiterating this problem because yesterday there were not many people in the class, so therefore I'm reiterating this problem. And at origin, you have an attractive Dirac Delta potential. So at origin, you have an attractive Dirac Delta potential given by minus V naught Dirac of x. Okay. Now, how to solve this particular differential equation? I yesterday also told you that in order to solve this differential equation, we will have to write the how to solve this Schrodinger equation. So we'll write the Schrodinger equation, that is d2 by d2 psi upon dx square minus hk square upon twice m. Then we have v as a function of x psi, and then you have e psi. Obviously, for all x less than minus d, your wave function would be equals to 0 because here potential is infinite. So there is no probability of finding the particle in this particular side. So for all x less than minus d, I'm not concerned. I'm concerned only for x greater than minus d right now. Okay. So I'm concerned with x greater than minus d. Okay. So it is the same problem that we were doing. I've just slightly changed the problem. Yesterday we were doing the same problem. I was saying that there is a wall or there is an infinite potential at x equal to 0. And at x equals to a. So I wrote yesterday minus v naught Dirac of x minus a. Okay, the same problem with a different sort of with a slightly different thing. Otherwise, the problem is same. Okay, don't worry about it. So this is what we have to do. So let us write the Schrodinger equation for all x greater than minus d. For all x greater than minus d, your vx can be written as minus v naught Dirac of x, and you have psi of x, and then you place minus e also here. Psi of x is equals to 0. And you have minus hk square upon twice m, and then you have d square psi upon dx square. So what I can do, I can write d square psi upon dx square plus 2m h ket square, and then you have v naught Dirac of x plus e psi x, okay, is equals to 0. And you all know that your energy is negative. So your energy is negative, so you can write E as equal to minus of modulus of E. All these things we have done yesterday itself. Okay. Now let us move a little bit ahead and try to write. What did we do yesterday? We tried to write the solution for all x not equals to 0, because at x equal to 0 this will become infinite, so it is not possible to write solution for x equal to 0. What we'll do, we'll write the solution for x, sorry, we cannot write the solution for x equal to 0. So what we'll say that we are going to write solution for x not equal to 0, because at x equal to 0 this will become infinite, so it is not possible to find solution for x equal to 0. So what we'll do, we'll try to find solution for all x not equal to 0, and if x is not equal to 0, then we may find the solutions in the vicinity of x equal to 0, or you can say in a range where your x equal to 0 is not contained. But we also know that your psi is a continuous function. Psi is a continuous function. So if you know your wave function to the left of 0, to the right of 0, then that will be equals to the value of function at 0. Because in any case, the physically realizable solutions to the Schrodinger equation must be continuous, must be single valued, and must be finite valued also. Even as x tends to plus minus infinity also, overall psi must be finite valued. So all these are conditions for the physical realizable solutions of the Schrodinger equation. Okay, so at x equal to 0, I cannot find the solution. So what I'll do, I'll go for something like x not equal to 0. Okay, so I'll go for something like x not equal to 0. So if x is not equal to 0, then this will be 0. So overall, this particular differential equation becomes d square psi upon dx square minus, I think I can write k square psi now, is equal to 0, where your k square would be equals to what? Your k square would be equals to 2m e modulus divided by h ket square. So instead of e, you will just write minus of modulus of e. This will be minus 2m e modulus upon h ket square. That particular thing you have written k square. And from the theory of differential equation, you know that this particular solution contains e ki power kx and e ki power minus kx. Both of these terms are contained. I think this is clear to you. Now,
sir, what is system, sir? Once can you please tell?
What? Sorry.
Sir, what's the system?
This is the system. Vx is equals to minus v naught Dirac of x for all x greater than minus d, and for all x less than minus d, your potential is infinite. The same question that we were doing yesterday, because Kalpana was not there yesterday, so I'm revising that thing with a slightly different version of the same. But it is the same. Yesterday, kya kar rahe the? Yesterday we were doing that at x equal to 0, you had an infinite potential. For all x less than 0, you had an infinite potential, and for all x greater than 0, you had a potential. You had this potential of Dirac delta attractive at x equal to a. Yesterday, the last problem.
Okay, sir.
Okay, and this problem for theoretical physicists is at times also called as an approximate model for problem of an atom near the wall. So your wall is this, where you have an infinite potential, and your atom is slightly close to the wall. So if you want to just write an approximate solution to such a problem without having any sort of interaction terms and all those things, so this is at times also referred to as an approximate model for problem of an atom near a wall. So this is the title of the problem that I'm giving to you, and this is a potential which we are concerned with right now. Okay, is that clear?
Yes.
Okay. Now see, yesterday I was discussing that e ki power minus kx plus e ki power kx is there, and just see what needs to be seen or what needs to be evaluated is certainly the possibility of what to write and what not to write. So, for example, if I say that x is greater than minus d, it will contain the solutions till infinity also. No, but the x greater than minus d implies x belongs to minus d comma infinity. So at t, as x tends to infinity, this cannot be there. This cannot be there. But if I write, sorry, for all x, my mistake, ed nahi hai, sorry. So this Dirac delta potential is this Dirac delta potential is at x equal to 0. Sorry. So for all x greater than 0, what I can do is, see, for example, now again, let me come back to the problem where I was. Okay, so we were writing the solution for all x not equal to 0, right? So for all x not equal to 0, this will be 0. And if this is 0, then your problem becomes d square psi upon dx square minus k square psi. Now, if at all the solutions are there for this particular problem, they can be written in some linear combination of e to the power minus kx plus e to the power kx. But then boundary condition needs to be also seen. So what is your boundary condition? Boundary condition number 1 is that for all x greater than 0, x tends to infinity will also come in this. So for all x greater than 0, can I write this particular thing? Can I write this particular thing? I cannot write this particular thing because as x tends to the infinity, this will blow up. So for all x greater than 0, only this remains a solution. And then there is a region which is here, this region. Here you already know that your wave function is 0, so don't worry about it. Now for this region, which is like I can write minus d to 0. So if x lies between minus d and 0, now here both of these wave functions can come. Right? Both of these solutions can be taken as wave function, isn't it? When some normalization constant would be there, forget about it. But overall, this will contain both e to the power minus kx plus e to the power kx. That is, if I want to write a solution for this particular interval, that is x lying between minus d to 0, both e to the power minus kx and e to the power kx can come. But for all x greater than 0, because for all x greater than 0, you have x tends to infinity also. And if x tends to infinity, this will blow up. So I can only keep this as a solution. Is that clear to you, both Alpana and Bharat? If a certain thing is not clear, please let me. I think certain mistake I've had. Acha. Okay. ठीक है, solution problem सब सही है. हाँ ठीक है, बोलो जी. Any problem? अल्पना को समझ में आ रहा है?
हाँ भैया.
ठीक है, चलो. So हम लोग क्या करेंगे? What are we going to do is we are going to write this solution piecewise. So for all x, I think if I'm not wrong, less than 0, greater than minus d, I can have both of these terms. So why not write some a e to the power kx, and then I can write plus b e to the power minus kx. This is what we wrote yesterday. And for all x greater than 0, I cannot afford this as a solution. So I will write only one solution, that is c e to the power minus of, I think, kx. Okay, is that clear? At times you can also drop these normalization constant because we are not concerned with this. Not much physical solution, not much physics can be extracted out of these normalization constants also. So at times you will find books not even writing all these things. Because ultimately, yesterday also we saw that this particular solution, this particular question can be solved only by a graphical approach. So hardly this particular constants would matter. But still, I have just mentioned so that it does not look sort of wrong solution to you. So I've just mentioned some arbitrary constants. Okay. Now there are two conditions. The first condition would be, the first condition to this thing is we should have a continuity. We should have continuity of wave function at x equal to 0. That is one part. So if my solution is continuous at x equal to 0, then c e to the power minus 0 should be equals to a plus b. That is, your a plus b should be equal to c. The first thing is this. Is that clear? Like x, if I write right hand limit to this 0, you have c e to the power minus k 0 plus h, and left hand you can write a e to the power k 0 minus h plus b e to the power minus k 0 minus h, and then you can write a plus b is equal to c. One thing is this. This is, I think, clear. And second thing, you can apply continuity condition at x equals to minus d also. So you know that for all x less than minus d, for all x less than minus d, your wave function must be 0 because you have an infinite potential there. So continuity of psi at x equals to minus d. So if I write continuity equations for x equal for psi x at x equals to minus d, then this will be a 0 is equal to a plus b. So it implies what? It implies your b should be equals to minus of a. Okay, so your potential is slightly changed. Your potential is slightly changed, and you can write what? You can write that your psi of x is equals to nothing, but it is equals to a e to the power kx, and your b comes out as minus a e to the power of what it came? Minus kx for all x lying between, I think. Okay. There is a mistake here somewhere. So at x equals to minus, exponential term is not there. So I'll write e to the power minus kd and then I will write e ki power kd, because if this comes to the case, then this will become 0. Okay, so e ki power minus kd plus b e ki power kd must be equal to 0. So it will not be the case. I'll write what? I'll write that e ki power minus kd plus b e ki power kd must be equal to 0. So this is your second equation, right? So I'll not write this, because otherwise I was just thinking about it. कि यार ये तो 0 use रहेगा. So no. Okay. So there are two conditions that we need to remember. So these two conditions are there. I'm just encircling them so that anytime we will want to use, these are the two sort of conditions that we have derived from the continuity of the wave function at x equal to 0 and at x equals to minus d. Is that clear to you? So your wave function is this. At x equals to minus d, left hand limit लोगे तो क्या आएगा? a e की पावर माइनस के डी, लेफ्ट हैंड लिमिट यहाँ लोगे तो क्या आएगा? b e की पावर के डी, और राइट हैंड लिमिट लोगे तो क्या आएगा? अच्छा, लेफ्ट हैंड लिमिट लेंगे तो क्या आएगा? 0 आएगा, बिकॉज एट एक्स इक्वल्स टू माइनस, एट एक्स लेस देन माइनस डी. ये देखो मैं आपको सुना देता हूँ. एक्स इक्वल्स टू माइनस डी के लेफ्ट पे, सो फ्रॉम द ऑन द लेफ्ट ऑफ एक्स इक्वल टू माइनस डी, योर वेव फंक्शन वाज 0, एंड टू द राइट ऑफ योर x equals to minus d, your wave function was this. Is that clear? तो लेफ्ट हैंड लिमिट क्या आ जाएगी? x equal to minus d पे 0, और राइट हैंड लिमिट क्या आ जाएगी? x equals to minus d पे this, a e की पावर माइनस के डी प्लस b e की पावर के डी इक्वल टू 0. इज दैट क्लियर? एक्चुअली है ना. तो ये दो बाउंड्री कंडीशंस आ गई बिकॉज ऑफ द कंटिन्यूटी ऑफ द psi x at x equals to 0 and x equals to minus d. Is that clear?
Yes.
Okay. Now, what would we do? Okay. So now what we do is, the third thing that we do actually is, whenever you have this these differential equations containing a Dirac Delta function, I will write it all over again because again there would be mistake. So this is that differential equation that we need to solve. So I'm just writing it all over again so that mistake now. If there is a mistake, then we'll not be able to solve it afterwards. So this is 2m. I think it is h get a square. And then you had, I think, v naught Dirac of x, and then I had, I think, plus e, and then I had psi, and then I had 0. Okay. And this is a differential equation that I'm writing for all x greater than minus d, and my Dirac delta function lies between lies at exactly at x equal to 0. So what I would do, I would integrate this particular differential equation from minus epsilon to plus epsilon. So what I will do, I will integrate this differential equation from minus epsilon to plus epsilon. So what does that give? What does that give to me? That will give to me d psi over dx from minus epsilon to plus epsilon. And then you have 2m upon h get ka square. And you know that this particular term does not vanish. So this particular term remains there. So this is 2m v naught. And this becomes psi of 0. And this particular term, when integrated from minus psi to plus psi, gets vanished. So you just see the last two lectures and you will come to know that I have done the same thing. So I'll not do it all over again. So if I integrate it from minus epsilon to plus epsilon, my second order derivative becomes the first order derivative. This particular thing, by filtering property of Dirac delta function, becomes this, and this particular term goes 0. Okay, so just kindly pause that lecture so that it does not bother you much. And this will be equals to psi dash epsilon minus psi dash minus epsilon plus 2m upon 2m v naught upon h get ka square, and then you have psi of 0. Also remember, I've told you yesterday itself that whether you write psi of 0, whether you write psi of epsilon, or whether you write psi of minus epsilon, in the limiting case epsilon tends to 0, all these things are equal because your wave function is continuous. Since your wave function is continuous, you go to the left of 0, you go to the right of 0, and you find the value of the function at 0. All three things are equal. Is that clear? Now what you can do, to the right of 0, let me see. Sorry. So to the right of 0, your equation is c e ki power minus k. So what I would do is, I would go again and write, here I would write psi dash means what? C e ki power minus k. So it will become minus k c e ki power minus k epsilon. Minus, to the left of 0, your equations are, I think I will write it, k a e की power, I think k minus epsilon it will become, right? And then you had, I think, minus ka e की power k epsilon, because you had a negative here. So negative comes up, minus epsilon you just write it. Is that clear? Have I made any mistake? Because if I make some mistake, then it will be too difficult for us to locate it all over again. So kindly check all these things. Keep checking all these things. Okay. Now, this particular expression, that is a e की power k like epsilon, and this particular term a e की power k epsilon. These are this is what? This is nothing but it is equals to what? This is equals to your. So I'll do it all over again. Okay. So overall, you've got this particular point. Is that clear to you? Is that clear?
Yes, sir.
Okay. Now, what I can do is probably what I can do is, okay. So what I would do, I would write all these terms. Yesterday, what I did, I just kept c e की power minus k epsilon. So what is c k e की power minus k epsilon? So I'll write it all over again. So you are here. Yeah, लिख देते हैं इसको. So your wave function was a e की power, I think kx plus b को मत लिखो, minus a e की power minus kx for all x less than 0 greater than minus t, and for all x greater than 0 you had c e की power, I think, minus kx. Is that clear? So if you just place epsilon here, so if you just place here, you will have a left epsilon, here you could write a right epsilon. So what I would do, c e की power minus k epsilon can be written as a e की power minus k epsilon, then I can write minus a e की power k epsilon here. Okay, so just taking just writing continuity conditions here, that is from the left of 0 to the left of 0 I'll write this. Okay, and to the right of 0 my wave function is this. So I'm just evaluating my continuity condition as x tends to 0. From the left I will write this wave function, and instead of x I will write minus epsilon because I'm approaching 0 from the left. And here I would write c e की power minus k epsilon. So instead of this, I will write this. And then I will write this minus k a e की power. I think this is negative. Is that so? Is
Yes,
that
sir.
negative? Minus negative.
Yes.
Minus k epsilon, minus k a e की power k epsilon. And then you have, I think, this particular term. This we'll intelligently use later on. Don't worry about it. We'll see how things unfold. Then I would, because I know that psi of 0 can as well be written as psi of epsilon, that is to the right of 0, and I can as well write to the left of 0. So that depends upon my overall structure of the question. So I'll see accordingly and write accordingly. So overall, you just see that these two terms, which two terms remain? So here is a negative. Here is a negative. So overall, what all terms remain? You have to see that also. Again, I have made a mistake somewhere. I don't know. Psi dash epsilon is fine. Minus k c e की power minus k epsilon, that is absolutely fine. And that is psi dash minus epsilon would give me k a e की power k epsilon. ठीक है, ये भी गलत नहीं है. Minus epsilon प्लेस करेंगे तो क्या आएगा? And then you have this minus k a e की power of k epsilon. Is that clear? मतलब कहीं गलती तो नहीं? Please check कर लो इसको. Otherwise दिक्कत आएगी. Just check this and just check this. I'm giving you a minute. Just try to check all these things. Are they clear? मतलब ये गलत तो नहीं है? Just see them. मतलब ये गलत नहीं होना चाहिए. Otherwise we'll not be able to figure out overall बाद में क्या गलती हो रही है. चेक कर लो एक बार, इसको फटाफट से चेक कर लो. ओवरऑल कोई गलती नहीं होनी चाहिए. दैट इज माय ओनली कंसर्न. So instead of c e की power minus k epsilon, I have written a e की power minus k epsilon. And right here, I have written minus a e की power. That is absolutely right. Then you have a minus. And psi dash means what? Differentiating this, so this will become k a e की power minus k epsilon. This is fine. And then you can write, this is minus, okay? Then you can write minus, okay? So there would be a So here is a negative, I think, right? Here it is a negative. So if I differentiate it, it will become positive, I think, right? Is that clear? See, देखो psi जो है ना, यहाँ पे देखो ध्यान से, psi जो था वो क्या था? Psi was this
Yes, sir.
differentiated. So this is like मूवी का एक भी नेगेटिव कह रहा हूँ दिक्कत हो जाएगी. So this will become minus k a e की पावर माइन. अच्छा ये माइनस नहीं था, ये तो प्लस ही था, सॉरी. This was minus, right? So this is a e की पावर kx, so this will become k a e की पावर kx, और x के लिए माइनस एप्सिलॉन रखो, यहाँ रखो माइनस के बी, और b ऑलरेडी क्या आया था, शायद माइनस ए आया था ना. अच्छा b माइनस ए नहीं आया था, राइट? तो a प्लस बी
Oh,
इक्वल सी था. तभी गलतियां हो रही है, और एक ये कंडीशन थी. So you had two condition, a e की power minus kd plus b e की power kd equal to 0 और a plus b equal to c. तो there are two conditions here. So एक मिनट वापस चलते हैं पीछे. ठीक है. So why am I writing this? Don't know. रोक दिया करो प्लीज, बीच में कहीं भी गलती हुआ कर बीच में बोल दिया करो, तो भाई इसमें वो बढ़ती जाएगी, फिर इसको समझना बहुत मुश्किल हो जाता है. मेरे लिए ये दिक्कत है कि मुझे बार बार ऊपर नीचे होना पड़ता है ना, तो इतने में मुझे समझ ही नहीं आता कि व्हाट एम आई डूइंग. चलो कोई नहीं, वापस करते हैं इसको. So I'll write on this page again my this wave function. चलो वापस लिखो इसको. So what यहाँ लिख रहा हूँ मैं wave function वापस. So this was a e की पावर kx plus b e की पावर minus kx. यही था wave function for all x less than 0 greater than t, and for all x greater than 0 your wave function was I think c e की पावर minus kx. Is that clear? यही था ना. करो differentiate इसको. To the right of 0 my derivative will be minus k, this will be c, this will be minus k, and this will be epsilon. ठीक है. To the left of your 0 your derivative will be k a e की power minus k epsilon, and then it will be minus k b e की power minus minus plus k epsilon. Is that clear? And this will be plus 2m b naught upon h ket square, and then this will be equal to psi of 0, this will be equal to 0. Is that clear to you? ये चीज समझ में आई?
yes.
Additionally conditions क्या क्या दे रखी हैं? One condition is a plus b equal to c, and एक और condition क्या दे रखी थी? I think एक condition और ही दे रखी है कि your
A is equal to minus b
a e की
exponential
पावर
minus
माइनस के डी प्लस बी ई की पावर के डी इज इक्वल्स टू 0. इज दैट क्लियर? ये था. ठीक है, डन. इज दैट क्लियर टू यू?
yes.
ओके. एक काम करते हैं, एक काम करते हैं, देखो व्हाट कैन वी डू. सी हियर यू कैन सी दैट overall this particular differential equation I have written a e की power kx plus b की power minus kx in solution in this format. What I can do at times, I can simplify this particular differential equation. हल्का सा just simplify, because see here there are no doubt there are three conditions. This is 1, this is 2, and this is 3. ठीक है. And then you have all you have, like, you don't know about psi, you know about psi, but then this will become all the more complicated. So for simplicity I'm writing, एक काम करो, just try to see if this works. For simplicity just write c equal to 1. Just write c equal to 1. So if you just write c equal to 1, at least one condition becomes easy, like a plus. Otherwise if you write this particular condition, your a would become c minus b, and again there would be another. So you, I mean, here there are two equations with a, b, and c, and you don't have three equations. So basically it will end up remaining somewhere in an unknown value. Are you getting my point? But if I don't simplify this expression, I will not be able to solve this. So a constant ko tum, you just assume something, so that at least this becomes easy for us. See, you have to find a and b, right? Your a plus b is c, which is another unknown constant. Your a and b are related by this expression. Okay, there are two ways of relating this. So just to ease your life, what you can do, you can take c equal to 1. Otherwise, there is another condition. You can use this condition also. But again, this condition involves too many like too many things up. So what I would do, I would just take c equal to 1 just for the simplicity, because I'm not concerned with ABCs. I'm concerned with something different. Is that clear? Can we take this?
Yes.
It will make our life easy, just to make our life easy. Just to make your life easy, I'm doing it. Otherwise, what can I do? I can write 2 in the yesterday manner also, but that I mean, that is too much to do. So what I would do is I'll take just c equal to 1 so that this becomes easy, and just find the solutions. So let us just try to find the solution. Now this will become minus k, and this is like b, this is like this. So you just take epsilon tends to 0. So what epsilon tends to 0 means, if I take epsilon tends to 0, this will go towards 1, this will go towards 1 and not bothered about it, this will go towards 1 and not bothered about it. So this will become k minus k, then you have minus ka, and then you have plus, I think, kb, and then you have this entire term, that is plus 2m v naught upon h ket square psi of 0 equal to 0. And let us just try to write psi of 0 also. So whether you write, so what you can do, if I have taken c is equal to 1, c is equal to 1, so your right hand side wave function, that is for all x greater than 0, your psi x can be written as, I think, e ki power minus kx. Now, if you want to write psi of 0, you can just take the limit to the right. So just take the limit to the right. So limit x tends to 0 plus e ki power minus kx should be equal to psi of 0. So this limit would be equal to, I think, 1. So just write psi of 0 as well, so that all of this becomes simple. All of these things become simple. So what I've done, I've written minus, I think this would be minus k minus ka. Then you have something like plus kb plus 2m v naught upon h ket square is equal to 0. Is that clear? And you have some extra conditions. Don't forget about it. These two are extra conditions. So there are 3 conditions that I've written. You have to solve all these conditions and find a b, at least a b, because c I have already taken some constant. Otherwise, मतलब यहाँ पर क्या होता है, यहाँ पे तुम्हारे पास 3 इक्वेशंस है, सॉरी 2 इक्वेशंस है, 3 अननोन्स है, तो मतलब इन एनी केस डिफिकल्ट हो जाता है. सो तो क्या करना, एक को किसी को कांस्टेंट मान लो, लाइक जस्ट कंसीडर वन एज अ कांस्टेंट, बिकॉज अल्टीमेटली वी आर इंटरेस्टेड इन फाइंडिंग द सॉल्यूशंस, है ना. So lately you will also find that the solution will be an approximate solution only, like we'll find from graph only. So hardly this value matters, so don't worry about it. Okay, is that clear to you? Now just try to find, मुझे जल्दी से बताओ what will be a, b and c. So I'm giving you 3 equations. Like I have given this equation 1, a plus b is again second, this is first equation, let's say this is your second equation, and third equation is a e ki power minus kd plus b e ki power kd is equal to 0. Actually, I was driven away by yesterday's solution. So yesterday we got b equal to minus a. If you remember yesterday problem, we were getting b equals to minus a. But now things have changed. So I was actually driven away by that problem. So I was doing something in between that only. So again, I've got remembered that my problem statement has changed now. Okay, is that clear? Now just try to find me the values of a and b from this. Just try to just pen chalao, just find a and b's from here, because we don't have much time left. So you have 3 things, a plus b equal to 1, then you have a e ki power minus kd plus b e ki power kd as 0, and then you have this term. So इसको थोड़ा simplify कर ही लेते हैं. So ये कितना हो जाएगा, I think minus ka plus kb, और इसको क्या करें, what I can do is a plus b equal to minus 1, तो एक काम करते हैं, a plus b minus 1, what I would do is minus k, and I can write b, a is equal to 1 minus b. So I have replaced the value of a in terms of b. That is a, I can write 1 minus b, and I have placed it here. So a, I have written 1 minus b, and I have placed it here. So I have minus k, this is minus 2k, and this is plus kb, and again plus kb. Okay, so I have 2kb is equals to plus 2m v naught upon h ket square. I have this equals to 0. Okay, and so b, what I can write is, okay, and here again, but again this will not give me anything, right? अच्छा, यहाँ से भी कुछ कर तो सकते हैं ना. I can write b e की पावर kd is equals to 1 minus b, and then they have a negative, right? So a की जगह क्या लिख सकते हैं? 1 minus b, so you have a negative 1 minus of b, and you can write e की power minus kd. Okay, so this is how you can do. And what it will yield you, I think it will yield you, uh, you have e की power minus kd here. Okay, you have e की power minus kd here, like in negative, right? You have it negative e की power minus kd. This will become positive, and उधर लेके जाओ तो क्या आएगा? b e की power kd, and then you have minus b e की power minus kd. Is that clear? I think this is clear to you. So what you can do, you can write b is equal to e की power minus kd, and instead of writing e की power minus kd, you just divide e की power kd. So you'll get a negative also. So I think this will be 1 minus e की power, I think 2 kd. Is that clear? इसको check करो एक बार. Just check it once. Is that clear? So your b becomes 1 upon 1 minus e की power 2 kd. Is that clear? And your a would become, I guess, if I'm not wrong, it will be 1 minus of b. So it is 1 minus of 1 minus of e की power 2 kd. So it will not yield me any results. So forget about this. I was trying initially at this, but this will not lend me any solution. So forget about this particular section. Just write this. So this will become 1 minus e की power minus kd minus 1. So this will become, I think, minus of e की power 2 kd. And then you have division of 1 minus of 2 kd. Just confirm these two. Bharat, is that clear? This is 1.
सर वो ऊपर वाली इक्वेशन कैसे लिखी आपने?
देखो, a plus b equal to 1. Fine. a e की power minus kd plus b e की power kd equal to 0. Done. So what I wrote that a को लिख b को लिख दो 1 minus of a. So you just write b as 1 minus of a and try to solve this. I think you will end up getting this. And if you find a, you will get this. Is that clear?
यस सर.
नहीं हुआ? कुछ गलती हो रही है?
नहीं सर, वो मैंने तो a प्लस बी, हाँ ठीक है, मैंने सॉल्व किया था, वो थोड़ा सा अलग आ रहा था सर इससे.
देखो, एक्चुअली a plus b equal to 0 नहीं होगा. That was yesterday's problem, right? So हमारा दिमाग
हाँ, a
उधर भी
प्लस
चला.
बी इक्वल टू 1 लिया है ना हमने इस बार.
a plus b equal to 1 लिया because c you cannot solve. तो basically c को हमने 1 ले लिया एक बार को.
राइट सर.
Okay, so these two are solutions, and third thing I will get is from the third equation. Third equation कहाँ गई? Where is the third equation? This is the third equation. So I'll write it all over again. The third equation is minus k. अभी अपन को ये तीनों solve करनी. minus k a plus k b plus 2m v naught upon h ket square, and then you have equal to 0. Is that clear? This is your third equation जो चल रही थी हमारी. याद करो. Just try to replace a as 1 minus of b. So what you will get, because now we know about b, so I can write minus k, and then you have plus kb, so you have plus 2kb is equals to minus 2m v naught upon h ket ka square. Okay, and b you can write as 1 minus of 1 upon 1 minus of 2kd. So I can write minus 2k plus 2k upon 1 minus of, I think, e की power 2kd is equals to minus of 2m v naught upon h ket square. Is that clear? I don't think there is an issue till now. Okay, and what I can do, I can solve it little bit. I think I can solve it little bit, and what I will get is I can take 2k common out, so I'll get, I think, this is minus 1 plus e की power 2kd, then you have plus 1, and then you have 1 minus of 2kd is equals to minus 2m v naught upon h ket square. And then I can write all this thing एक separate जगह पे. This negative, this gets cancelled. Okay, is that clear? This gets cancelled. I have no issues about it. इसमें किसी को कोई issue? Or what I can do is this 2 gets cancelled. Forget about this. Now you have a k here. You have a k here, and 2kd just divide it and take a negative. So take a negative and divide it. So I think I will get k upon e की power, no, sorry, you will get 1 minus of e की power minus 2kd is equals to mv naught upon h ket square. Is that clear? I don't think there is an issue till now.
यस सर. Yes,
right?
sir.
So your K would become, I think, mv naught upon hkt square 1 minus of e to the power minus 2kd. This is what
Yes,
we
sir.
got yesterday also. If you remember, instead of d, we had a there. So I was telling this is the same problem. So now, yesterday we did this problem. This problem, I'll reinitiate this problem solution in the next lecture. But just reiterating, we are doing a problem which is called as an approximate model of atom near a wall. So this is your wall, which is situated at x equals to minus d, because beyond it your potential is infinite, and here your potential is centered at 0, and that happens to be an attractive Dirac delta potential. So your atom is sitting here. It is at a distance of d from the wall, and at x equal to minus d, this wall, what wall represents an infinite potential. So you have an infinite potential here. Your psi is 0. So we've got till now the solutions of A, B, and K's, and the wave function was this. So just remember, okay, here it is. Okay, so we are going to do it in the next session.